I'm going to do another exercise to constructing a hidden Markov model given, I'm going to just, given a multiple sequence alignment. How do we construct a hidden Markov model for that? Okay, this was a midterm question. And it's worth 20 points out of 100. Okay, so again, we have 5 sequences, similar to the example we had, but a little bit different. So it looks like this. The first column is A gap, and C gap, C, and I have G, A, G, and T, gap, and all A's, and gap, G, and all T's. Okay, so the question is like this. Consider the multiple sequence alignment of 5 DNA sequences given below. Draw a profile hidden Markov model for these 5 sequences. You may use any number of match, insert, delete states you want. You may omit some states of the HMM if you believe that they are not required for the sequences given. And give the emission probabilities at each state and the transition probabilities between every state in your hidden Markov model. Again, if those probabilities are 0, you don't need to show them. And here are some important notes. A column in the multiple sequence alignment is considered a match state if the majority of the rows in that column is non-gap. If we have a column with majority of the rows non-gap, then we consider it as a match state. So we should be given this rule in order to determine the match state. Such a rule should be given. For example, I may change the rule saying that if all of the rows have the same type of nucleotide, I consider it as a match state. This is a different rule. In this different rule, only, for example, maybe this one, ignoring gaps, if all the nucleotides in the column are the same nucleotide, then treat it as a match column, and then it will be this one, and this one. I would have 5, but this one would not be considered as a match state because there's an A here, if I had that rule. But here, in this question, the rule states that if a column has majority of rows non-gap rows, we consider it as a match state. In other words, this is going to be a match state, match. Okay, the only thing I don't have a match state here is going to be this column, because that's the only column in which I have gaps, majority gaps. Now, in other words, after the first thing you need to do is determine how many match states you are going to have. And in this example, we are going to have 6 of them, 6 match states. And it also says, as I know, do not use pseudo counts when determining the emission probabilities or transition probabilities. Do not use pseudo counts. Just exactly use all the data here. You can use 0 probabilities if you do not observe anything. Now, here's how we are going to proceed. We first draw our 6 match states. I'm going to, okay, M1, M2, M3, M4, M5, and M6. What you can do is, you can ignore the begin and end states and say that with 1% probability, I'm going to start at this, okay, with 1.0 probability. 100% chance I'm going to start with this. Or what you can say is you can have a begin state, a begin and an end state to mark the end of these sequences. Now, from the begin state, we are somewhere here. This is our begin state, starting for all the sequences. The first thing is to find the transition probabilities from begin to M1 or begin to something else. We may have delete states or insert states, okay? For example, delete 1. Here, if we immediately by looking at these sequences, we see that we have a sequence here which skip the match 1 state. So we need to visit the delete state. We need to have a transition which is going to take you to M2. And we do it by this M1 state, okay? So now we need to decide from the begin state there are 2 possible transitions. And 4 of them go to M1 state, and 1 of them goes to M2 state. And therefore, with 0.8, this 0.2 transition probability, we are going to have a transition like that. And at M1, I'm going to have the emission probability of A to be 1.0, because that's the only nucleotide I observe at this first column. And now, from the second match state, actually from the first match state, for these 4 sequences which have visited the match state, in order to determine the transition out of that is outgoing the match state, I only need to consider the sequences that have visited that match state. So when finding the transition probability that are outgoing from M1 state, I'm going to ignore the last sequence because it doesn't visit the M1 state at all. There is no M1 transition that will happen in this state. So, and for these M1 transitions, I have M1 to M2, M1 to M2. So these are all possible M1 to something transitions I observe in this alignment. I have 4 of them. 3 of them are to M2, 1 of them is to M3. Okay, it looks like this. Out of these are the places that I visited the M1 state, and 3 of them goes to M2 state, match state 2. Let me also write them here below. And 1 of them skips that state, M1 state. Okay, so I can say I'm going to have, actually I can also, I'm going to need another delete state here. Let me name it delete 2. Okay. And this is going to be 0.75. This is going to be 0.25. Out of the 2 possible arcs going from M1, 3 of them go to M2, 1 of them go to delete state, and we have, what we have here is 1.0. If you come to a delete state, you immediately go to the next available match state, because from that delete state, after we visit the delete state, for certain we go to this match state 2, and if we visit this delete state, we directly go to match state 3. And in this match state 3, everyone visits this match state 3. Right now we are at match state 2. If you want to find out what happens, the outgoing transitions from match state 2, we need to consider these 4 sequences which have visited match state 2, and all of them go to match state 3. In other words, I'm going to have here 1.0, and the match state 2, my transition probability for C is 1.0. And match state 3, I have 0.8G and 0.2A. These are my emission probabilities. Now, up to this point, now you can say, you can check your hidden Markov model. Up to this point, after this point, you're going to solve a different problem, because at that point, every sequence has visited match state 3. You start from new. I mean, meaning that, I mean, after that point, you are solving like a different problem, a continuing problem. Everybody's now it's like a synchronization point. It's like everybody's now match state 3. Now let's see what will happen after that. After match state 3, 4 of the sequences go to match state 4. 1 of them skips that sequence, match state 4. So I'm going to need another delete sequence. Let me name it delete 3. So it's going to be like this, 0.8, 0.2. 4 of them visit that. And from that delete state, I go to match state 4 for sure, again 1.0. And from the match state 4, the sequences that have visited match state 4, all of them go to match state 5. It's going to be like this, 1.0. Match state 4 is all T's, 1.0 T. And match state 5 is 1.0 A. Now, from this match state 5, one sequence go to an insert state. Okay? This G here, this is not a conserved column. You cannot say that these sequences skip something. They're not skipping anything. Okay? These 4 sequences go from match state 5 to match state 6 directly. So they're not skipping anything. One thing that's happening interesting is that this last sequence is inserting something. So I need an insert state here. One of the sequences, 0.2, 0.8, is going to an insert state. Okay? And at that insert state, it's going to directly go to the match state 6, because after that insert state, we only have one transition from insert state to match state 6. And at that insert state, you may say that the emission probabilities at insert states are 0.25, 0.25, 0. All of them are equal probability. You can observe any nucleotide with equal probability at an insert state. Okay? That's the different thing in match states. We were using the frequencies of amino acids we observed at the columns. But this G, since it's not really important whether it's a G or a T or an A, something is inserted there. Okay? To account for that fact, we just say you could have seen anything with equal probability there for an insert state. That's the difference of insert states from match states. For match states, we use the real frequencies. For insert state, we just say you could have observed anything. And M6, we have 1.0 T, and then we have 1.0 to N. So this is our hidden Markov model for this alignment, okay, which has the delete state, insert state, and match state. So we have all these 3 types of states in our model without the pseudo counts. This is what we have. Any questions? Yeah. Yeah, the emission probabilities in an insert state is always going to be same, regardless of any insert state. The important thing of the insert state will be the transition probability. What is the self-transition probability? Which is going to determine the length of insert. If we have a higher self-transition probability, we are going to have a likely higher number of inserts. That's the important thing. That's the thing that differs between insert state to insert state, the self-transition probability. Other than that, the emission probabilities in all insert states are going to be equal. But again, this is a design choice. You could have said that, okay, I also may have certain insert regions may have different characteristics. For example, I may have an insert region which is GC rich, okay, CG, or I don't know how is it called conventionally, GC rich, okay. So it's GC, it may be a GC rich region, okay, which means that in that insert part I have lots of GCs. And in that case, if you want to model such an insert region, you may give higher emission probabilities to G and C compared to A and T. So it's just, as I said, it's a design choice. Okay, so let's continue. Yeah.
As an implementation aspect, if you want to try to make this model, for example, in the column 1 of the example, in the second sequence we have gap instead of A. For sure, from the start button, first we made some assumption from going to start to the match. If we want to propagate to the second match state, then the probabilities of the start to the second match will be updated in that case.
Okay, so you are saying instead of having this first delete state, I could have a transition from begin state to M2 state directly.
Of that we had gap instead of A.
Yeah.
And in the
Yeah.
implementation aspect, we would update the previous probabilities.
Yeah.
It would be like this.
Yeah. So in your programming assignment, you'll do something like this automatically. Given I'm going to give you, so this is what I did by hand here. You're going to write a program which is going to generate this model given a protein sequence or DNA sequence alignment like this. You are going to write a program to generate this model. Okay, this is going to be difficult because you need to also decide. Generating this model is not just visualize, drawing it on screen. Your goal is not to draw this model on screen. You need to decide, you are going to represent them as formally in some arrays, for example. There may be a state array, a transition table. It will be a sparse table. You're not going to have all the transition from all the states, but you are going to have a transition table, a transition matrix, which has these transition probabilities. You're also going to have an emission probability matrix for each state. The transition matrix is going to be a square matrix, but the emission matrix is not going to be a square matrix. It's going to be the number of rows can be your states, and the number of columns may be the symbols that are emitted. Okay, so you can have a rectangular matrix like this, and all you need are these actually. The set of states as an array, and two tables, transition matrix and an emission matrix. Having these things, you have your hidden Markov model. So your goal is to fill out these tables with correct values. Okay, now I skipped actually a couple of slides. I'm not going to talk about pseudo counts that much. Okay, you get the idea what the property. The main reason we use pseudo counts is that if you observe something else other than A, you don't want to have zero probability here. But for your assignment, you're not going to use pseudo counts. If you have a sequence we do not observe this A, we are going to have zero probability for that sequence. Again, just for ease of implementation, you are already doing a difficult thing. I don't want to make it more difficult, so we are going to ignore pseudo counts in the assignment. Now, after we have such a hidden Markov model, the next thing we try to answer is, given a new sequence, which is not aligned with this multiple sequence alignment. We have a new sequence with no gaps and anything. Okay, it's just that we have a completely new sequence. Now our goal is to find out what is the probability that this hidden Markov model generated this sequence. This is scoring a sequence against the profile hidden Markov model. So this sequence may have been generated by a number of paths. I mean, this is not true for the multiple sequence alignment. The multiple sequence alignment directly tells us the path that generated this sequence, because the way we put these gaps and put these columns shows us, and these deciding that this is M1, M2, M3, M4, we decide that this T is emitted by this M4. A multiple sequence alignment fixes this path. However, if we have a sequence which is not aligned to these sequences, we don't know whether the first A is going to be emitted by an insert state, match state, or whether we are skipping. So there may be multiple paths through this hidden Markov model that have generated the same sequence. In order to, and the path probability, the probability of a specific path is the multiplication of all probabilities, emission, transition probabilities, along the path. That is going to be the probability of a single path. If there are multiple paths that could have generated the same sequence, the probability of observing that sequence from this hidden Markov model is going to be the summation of all these probabilities. Okay, so it's the summation. If there are multiple, if there's a single path with this probability, and if there's another path with another probability that may have generated the same sequence, the total probability of observing this sequence is going to be the summation of these two probabilities. So in order to answer this question, what is the probability that this hidden Markov model generated this sequence, we need to find all the paths that may have generated this sequence, compute their probabilities, and sum them up. Okay, this is how you solve the question. And another thing is, another question we may ask is, out of these all possible paths, which one is the most likely path? Each one have an associated probability. What is the path with maximum probability? We can also find this. And the solution to both of these answers use the same algorithm. In the first algorithm, we just sum these probabilities when we are going along the path. We sum the probabilities. And in the second case, in the second problem in which we are interested in the maximum probability path, we just keep the maximum values, which is going to give us the maximum valued path. The only difference between these two algorithms would be, one of them will be keeping the maximum of some probabilities. The other is going to be adding up these probabilities. Then summation and maximum, only a simple mathematical operator, is that will be the difference between these two algorithms. Okay, so we are going to use a dynamic programming solution. I'm going to describe the dynamic probability solution for this. And first start with the Viterbi algorithm, which uses this maximum, which just retains the maximum probability path. And at the end, it gives us the probability of the path which is most likely to generate this sequence. And similar to the sequence alignment algorithm, the sequence alignment algorithm gives you a score, but by tracing back, you are able to generate the alignment. And in this case as well, in the Viterbi algorithm, in addition to the probability of that path, we can actually find what that path is. What is the most likely path that generated this sequence? Now, the dynamic programming algorithm is based on certain assumptions. At any time, the process we are modeling is in some state. So at any time, we need to be at, and this is done, these assumptions are all met by the profile hidden Markov models we have discussed. We have finite number of states. Each state produces a single output. And computing the most and this is the most interesting assumption that we need to think on. Computing the most likely hidden sequence up to a certain point t must depend only on the observed event at point t and the most likely sequence at point t minus 1. So it tells us that this assumption helps us to divide the problem into smaller problems. In other words, if somebody told you that, given a sequence like this, okay, if somebody told you that the most likely paths that produce ACG is this, okay, if somebody told you the best path that could have generated ACG is this path, starting match state, delete state, insert state. If somebody gives you this path, this assumption tells you that by looking at the next symbol, and if I know this path, the most likely path that is going to produce ACGT can be found easily. Okay, in order to find, if I know the most likely paths that have generated this ACG, I can extend this most likely path by after observing this new letter t. The most likely path that generate this ACGT only depends on this path and the emission probability of t. Okay, so this is observed event point, and also we may also need to have the transition probability from this, whatever this most likely state is. By looking at the transition probabilities from this state and to the other states, we can find the most likely path that could have generated ACGT. In other words, like this. I have solved a partial problem. I have found the path that have produced ACG, the most likely path, the best path that could have generated, the most likely path that could have generated ACG. The most likely path ends at a specific state, right? For example, this G is most likely generated by M3 state. In order to find out what is the most likely path that generated ACGT, all I need to do is this. From that M3, which states I can go to? From that M3, I can go to an insert state, I4 maybe, or I may go to another match state, M4, or I may go to a delete state, D4. Okay? From that M3, if you can go to 3 states. Each of these choices have associated transition probabilities, right? And each of these also states have associated emission probabilities. An insertion state has an emission probability of T, and a match state also has an emission probability of T. By multiplying these transition probabilities and emission probabilities with the probability that I have found up to now, and by choosing among the, by comparing these probabilities, by choosing the best upon them, I can extend this path 1 letter more. So this is what we are going to do. We are going to continue doing this by, but we need to again consider, we are not going to, this is not going to be a linear algorithm. We are not going to be able to grow the path 1 by 1. We need to consider all possibilities when we are doing that. And all these assumptions are satisfied actually by our profile hidden Markov model. And the first order hidden Markov model means that the transition probability matrix is a 2-dimensional matrix. That basically it means that the next state you are going to go is determined by the current state you are in, right? This is what the transition probability matrix tells us. It tells us that if you are currently at M3, with this probability you are going to be at M4 in the next state. With this probability you are going to be at I4. The fact that the choice where we are going to be next is determined where we are currently. If we had a different transition matrix which used both the current state I'm in and the previous state I was in, okay, instead of a transition matrix, imagine we have a transition cube, a 3-dimensional transition matrix based on the first state and the current state and the previous state, you determine the next state. So it will be something like this. Given 2 states, what state you are going to be next. The current matrix is like this. The current transition function acts on a single state. Based on the current state we are in, what state we are going to be. The current transition is like this. This is called the first order HMM. And there may be also second order HMMs in which looks at 2 previous states by looking at where you are currently and where you are previously, determining the next state based on this. If you do that, it's going to be a much difficult problem. We will not be able to solve this. I mean, this assumption is going to be violated. Okay. Now, here is the algorithm. Okay. Again, when I talk about a dynamic programming algorithm, is just a set of recurrence relations. You should not expect a pseudocode that tells you how to fill a table when you are looking at a dynamic programming solution. This is the complete solution to the problem that we have talked about. So let's see what this tells us. First of all, we need to define what this VMU means. Okay, we need to define our variables in this equation. Again, just this definition is not enough. We need to define what they correspond to. So this VUMUXI means that the path, the probability of a path that ends by transmitting the ith character of the sequence. So X here is a vector of observed amino acids. So the X is a vector of, it's our protein sequence basically. X is our protein sequence, and XI denotes the ith amino acid in that sequence. So that sequence has a certain order starting from 1 goes to n. Okay, so XI denotes the ith amino acid. MU denotes the uth match state U. And this VMUXI is the probability of the best path that have generated our protein sequences up to the ith amino acids, including the ith amino acids. Okay, so this is how we define V. V is the probability of the best path that have generated the first I amino acids of our protein sequence. Now, what this tells us that, this equation tells us that the probability of this best path is actually the multiplication of the emission probability. Actually, this one says that. Okay, this is also important. I actually missed a very important point here. The probability of the best path that is going to end at match state U. Okay, we decide something here when we are doing something. So it's like this. When we have this ACG, this T, I mean, we may at this point this ACGT, this path, there may be multiple paths in which the last state is different. This last T may have been emitted by a match state, it may be emitted by an insert state, so we are still going to be considering multiple paths. We are not deciding on a single path when we omit this yet, okay? Because we do not know, maybe we cannot decide on a specific path, because considering the remaining sequences, this specific choice may be a wrong choice, okay? We do not decide on a specific path initially. So this DP algorithm considers all paths that ends at different states. So at this point, ACGT, so if I want to write V, for example, MU, this T, okay, this the probability of a path, probability of the path, best path that ends at the match state U. Okay, I may have another probability, a different path which ends at insertion state U. I need to consider both of these paths, because since I do not know what will happen at for the rest of these sequences, for the AT part, maybe this path is going, if you consider overall sequences, this path is going to be maybe better, or this path is going to be better. Okay, I do not know that yet. So at each step, I need to maintain all the paths that end at all these possible states. So this V mu xi shows me the probability of the best path that ends at mu state, which have emitted that ith amino acid sequence. And that probability is found like this. It found what is the probability of emitting xi at that match state, the emission probability of xi at that mu state, times the maximum of these three things. The maximum of these three things determine basically where you could have come to this mu state. So to this mu state, there may be multiple paths that could have lead you to the same state. And we need to consider all these multiple paths that could have led me to that state. And this one chooses the best of those as the best path that ends at mu. Okay? Now we can make a decision at this point if I want to find that what is the best path that ends at mu. I consider all the paths before mu, and I choose the best of these three paths that will lead me to a path that ends at state mu, which have emitted the ith amino acids. Okay, and this is basically in this max term, we are going to have terms which relates to the possible paths that could have preceded the mu state. Which states can come directly at time t minus 1? Which states can I be before coming to mu? Okay, and in this, yes?
Is it possible for a base or amino acid to be in a max state or in an insertion state?
Yeah, it's possible. Not in both. I mean, both paths may be possible, but one of those paths is going to be either, they may be equally likely, but the actual process that generated the observed sequence use one of them. Okay, the actual process generated has been one of these states and generated these amino acids. Two states cannot generate the same column. Meaning that they may be two paths may be equally likely, two states may be equally likely, but we are going to choose among one of them if we are going to actually generate that amino acid sequence.
So in this example, if we have a match state for T,
Mm-hmm.
but if insertion state, if we use insertion state,
Mm-hmm.
it will not be T, right?
Maybe, yeah. T will have a certain probability. At that insertion state, we may also have a probability. Right now, what we are doing is, we are just computing a probability. What could have happened, what would be the probability if I followed this path? If following that path is impossible, that probability is going to be 0. You would not even go to that path. But if it's possible to observe a T at that insertion state, we are going to consider that. We are going to consider all states here. But the good thing about a dynamic programming algorithm is when we are considering these all states, there may be multiple paths that lead to a certain part, but that multiple paths is not going to be very parallel. This is a very important observation. If I'm interested in paths that end at the match state U, if I'm interested in paths that are going to end up at this specific state, the number of previous paths cannot be, I may not have more than 3 choices considering the place that I visited before MU. Because of the structure of this hidden Markov profile, hidden Markov model, if you are going to come to MU at that point, you have to be, this is for sure, you have to be in one of these 3 states. Therefore, you restrict your multiple paths to, you restrict your choices to a small number when considering only the previous time step. It's like this. When you may have multiple paths, and I'm going to end here, we are going to continue this next week. The number of paths from a certain, between, these are our states, we can have, so imagine this was a graph, okay? If we have a graph like this, the number of paths between this node X and this node Y can be huge, okay? However, in a profile hidden Markov model, we don't have a structure like this. We have something like this. Since it's a first order hidden Markov model, what we have is something like this. It looks more like this. We have multiple paths, but if I'm going to consider just this node and the previous node that could have occurred before this node, I have only 3 options, okay? If I know the best path up to this point, by using only these 3 choices, I can find out the best path that ends at this node. Okay, this parallelism, the number of paths that I can have between 2 consecutive nodes is not going to be that much. It's going to be in this profile of the Markov model, these equations tell me that it's only 3. For a match state, in order to come to a match state, you can be in 3 previous different positions. You can either be in a previous match state, or in a previous delete state, or a previous insert state. Those are the only possible things. You cannot come to this match state from match state 1. Okay? You cannot immediately go from match state 1 to match state 5, for example. If you're at match state 5, you need to be either match state 4 previously, delete state 4, or insert state 4. So this is what this dynamic programming recurrence relation gives us, and that's the whole algorithm. This is the transition probability that from that previous state to the match state, and this V is the probability of best path that ends at that insertion state, for example, and that emitted the symbol x I minus 1. Okay, so we are going to continue this, and I'm going to solve an example on the how do we fill this table, and that's going to conclude the hidden Markov model subject.